recently moved from New York back to the UK, to the University of Manchester. And I'm going to be talking about how we can use simulations to help understand how robust our observational inference methods are. So the motivation for this is really the exciting spectroscopic data that we're getting from JWST. And we actually haven't heard much about massive quenched galaxies this week. But JWST is really enabling constraints on the star formation histories of quite high redshift quenched galaxies, including redder, fainter sources that were previously hard to study. And I'm showing here a figure from some observational work by Adam Carnell, where they got really high quality spectra for 5 massive quiescent galaxies above redshift 3. They fit these JWST spectra with bagpipes, which is a commonly used SED fitting code, assuming a double power law history. And they then integrate this inferred star formation rate history here to get an inferred stellar mass assembly history here on the right. And the source shown here in green is this interesting source that was also studied by Carl Glazebrook. This is at redshift 3.2, so towards the lower end of these high redshift quiescent galaxies. But the interesting thing here is that the stars appear to have assembled really quite early. And what Glazebrook was arguing is that a stellar mass of this amount by this high redshift could actually be challenging Lambda-CDM. The red contours here are from some work that went further and tried to kind of compare this inferred stellar mass assembly history in green to expectations from halo modeling. So this is kind of expectations for the mass of the most massive dark matter halo within the survey volume, scaled to the most massive galaxy, assuming some conversion from dark matter to stars. And the left-hand panel shows kind of a fiducial star formation efficiency using the six-stream value statistics model that Chris Lovell implemented. And then the right-hand panel shows a model in which all available baryons are converted to stars, so 100% star formation efficiency. So, you know, the green kind of 1 sigma contours are well above the expectation values at around redshift 8 for the fiducial model, potentially indicating that we need very high early star formation efficiency for these massive galaxies. But taking kind of a step back, this is how we go about getting this best estimate of the stellar mass assembly history using a fitted spectrum. So we take our spectrum, we have our star formation history, and we just integrate. But one assumption in this, when we do this integration, is that all of the stellar mass was formed in situ. So in the work I want to present now, I'm going to kind of use simulations to ask how reasonable is this, and how much of an effect does this assumption have on our derived stellar mass histories. So for this, I'm going to use the illustrious TNG simulations. First of all, just to check we're in the ballpark of kind of correct numbers of quiescent galaxies, I'm showing here stellar mass functions for star forming in blue and quiescent galaxies in red. So the observational estimates are shown with these dash points. These are estimates from Derek McLeod. And then the lines show the TNG model. And on the left, I'm showing TNG 100, and on the right, TNG 300. And actually, the mass functions don't look too bad at the high mass end, perhaps surprisingly. Though, you know, this only goes up to about redshift 3.2. So luckily, okay for our redshift 3 galaxy. When you go to significantly higher redshifts, you start really under-predicting the number of quenched galaxies. So from a simulation like TNG, we can extract massive descending galaxies at a redshift similar to our observed sources, and then track back their assembly histories using the subhalo merger trees. So here I'm showing stellar mass histories for the 3 most massive galaxies in the TNG 100 box at redshift 3, so Galaxy 0, Galaxy 1, and Galaxy 2. And these galaxies all by redshift 3 reach above 10 to the 11 solar masses. And in red I'm showing the formation times of all the stars that are in that galaxy by redshift 3. So I'm calling this kind of the archaeological measurement. as it's what you'd infer from observations in the ideal case. So if you could, correctly measure the age of all the stars, this is what you'd get. And in blue, I'm showing the actual mass of the most massive individual progenitor. And all these little red points at the bottom show the individual, more minor progenitors that eventually merge into this massive galaxy. And you can immediately see that there's actually quite a big difference between this individual massive progenitor and the archaeological measurement, the sum of all progenitors. So this bottom panel here shows the red line divided by the blue line. So this is what I'm calling kind of the bias in the inferred mass of the single progenitor that you get if you assume that all that mass formed in situ, like we have to do with the observations. And this just really reflects the fact that you can't necessarily distinguish stars formed in situ from stars formed ex situ in your star formation history fit to the spectrum. And you can also see that there's actually quite a significant difference between these three galaxies. So even at similar mass, similar redshift, and this is reflecting just a wide range of assembly histories. So I repeated this for descendant galaxies at different redshifts. So this figure is showing this bias versus redshift for descendant galaxies at redshift 1, redshift 2, redshift 3, and redshift 4. And for descendants at a given redshift, the ratio of this archaeological to single progenitor mass increases with look-back time. So towards higher redshifts, it kind of becomes harder to reconstruct the mass history of a single source. Also, the magnitude of this bias is more severe for lower redshift observed sources. So we get higher at redshift 1 than at redshift 4. And this is just because these galaxies have had more time to undergo mergers. We can also look at which galaxies are most affected by this effect. So here, for every descendant galaxy at redshift 3, so not just the most massive this time, I'm calculating the maximum value of archaeological mass over single progenitor mass, which I'm naming here the kind of maximum bias, so the kind of peak on that plot. And on this slide, I'm showing maximum bias versus stellar mass versus half mass radius and versus mass weighted age. And the different colored lines with shading show different halo mass bins. So we find kind of significant trends with halo mass, but actually once you take out the halo mass effect, not such significant trends with any other property. So our redshift 3 galaxies that are hosted by higher mass halos show the strongest maximum bias. Actually, just because of the link between stellar mass and halo mass, since stellar mass is observable, I'm just plotting the final descendant galaxy mass versus this bias at different look-back times for descendants at redshift 1, and you can see that there is like a slight trend with stellar mass. And aside here, I've done some convergence tests, to check that the resolution of TNG 100 is sufficient for this study. So here I'm showing the same plot, but the dashed lines show TNG 50. So it's always a balance between resolution and statistics. So I choose TNG 100, but actually this is kind of validating that the resolution is fine. If you try to use TNG 300 for this, though, the agreement is quite poor. So here in dashed lines, I'm showing TNG 300, and the solid lines are showing TNG 100. And this is because TNG 300 just doesn't have the resolution to kind of capture those major mergers and quantify the ex situ fraction properly. And this is potentially interesting in light of some recent work with Flamingo, where they kind of found that quiescent galaxies did seem to be built in situ, because that has an even lower particle mass resolution. But really the idea of this project is to kind of derive an approximate correction for this bias to account for your ex situ assembly when you're inferring stellar mass histories for observed sources. So here I've derived kind of an average correction for galaxies above 10 to the 11 solar masses at redshift 3 and applied that to the source studied in Carl Glazerick's paper. And you can see that this correction moves just the 1 sigma stellar mass assembly history contour kind of right down, potentially into reasonable agreement with the extreme value statistics halo model. So this is potentially an alternative explanation, doesn't challenge lambda CDM or require very extreme star formation efficiencies, though, of course, there are many other arguments that we might need elevated star formation efficiencies in the early universe. So this is a little summary of this part of the talk. Basically, fundamental uncertainties in merger histories are really an impediment to robust stellar mass histories for individual sources. This is really potentially favoring comparisons like stellar mass functions, where you're comparing masses at the time you're measuring them, rather than some kind of inferred past value. If I have a little bit of time left, I want to present some work investigating in a bit more detail the challenges of matching numbers of quiescent galaxies in simulations. So this right-hand plot is showing some observations from JWST, and note that there's actually still a huge amount of scatter in these observations. This is number density of massive quiescent galaxies as a function of redshift, and then a few lines here are showing some model predictions. So from Eagle, Flirt, and the Santa Cruz SAM. And you can see that, as things stand, we're under-predicting numbers of high-mass quiescent galaxies, particularly above redshift 4. And another population that's been difficult to match in simulations is submillimeter galaxies. And we think there may be some evolutionary link between quiescent and submillimeter galaxies. This paper from Chris Hayward a few years ago illustrated this persistent challenge of matching both submillimeter galaxy number counts and quenched galaxy fractions. On the left, you can see 850 micron submillimeter counts. The points show the data. The black line shows the prediction from illustrious TNG, and the blue line shows the prediction from illustrious, where you attain the submillimeter flux density from some scaling between dust mass and star formation rate. And actually, the original illustrious model, not the TNG model, matches the submillimeter counts a bit better. But if you look at the main sequence plots on the right-hand side, this is illustrious TNG. TNG is doing much better at matching this population of massive quiescent galaxies. So a student I was working with who actually just defended his thesis yesterday, Pablo Araya, used the MCMC mode of L galaxies to investigate whether he could find some model that was able to reproduce both of these populations. And he did this by actually using submillimeter counts and quenched galaxy fractions as a constraint in the calibration process. So Pablo was actually able to find, perhaps surprisingly, a decent model that matched the submillimeter number counts quite well. So this is all of his experimentation, and he's managing to hit these number counts. He also manages to produce populations of massive quiescent galaxies. So this is redshift 2, 3, and 4. You can kind of see this box of what he's defined as a massive quiescent galaxy, and you see we are getting them out to redshift 4. He doesn't quite hit those high observed fractions yet, but he's consistent with the lower limits. To do this, he needed to have quite a high star formation efficiency in galaxy mergers, and he also needed to have quite high efficiency of accretion of coal gas onto the black hole. So we can use this calibrated model to try and understand the evolutionary link between bright submillimeter galaxies and early quiescent populations. So shown here on the top panel is the maximum 870 micron flux density reached by progenitors of massive quiescent galaxies at redshift 2, 3, and 4. And Pablo finds actually that 90% of these massive quiescent galaxies that he's simulating actually exceed a millijansky at some point in their history. And this lower panel is showing exactly what point in their history did they reach that maximum submillimeter flux density. So redshift 2 quiescent galaxies were on average submillimeter bright at about redshift 3.4. Redshift 3 quiescent galaxies were submillimeter bright on average redshift 4.3. And redshift 4 quiescent galaxies were on average submillimeter bright at redshift 5.5. In general, fairly short timescales before they're observed as massive quiescent. But we can also look at the broader submillimeter galaxy population and ask when galaxies that are submillimeter bright actually quench. So taking this left-hand panel of submillimeter galaxies at redshift 3.4 as an example, and plotting the cumulative quench fraction versus redshift for these galaxies split by submillimeter flux density at redshift 3.4. So galaxies that are 1 to 3 millijansky at 170 micron are in navy. And you can see that if you select galaxies at redshift 3.4, actually only 10% of those are quenched by redshift 2. So although the epoch of submillimeter brightness of massive quenched galaxies at redshift 2 was 3.4, most of those submillimeter galaxies at redshift 3.4 are not quenched by redshift 2. This is the same for submillimeter galaxies selected at higher redshifts. And interestingly, the brighter submillimeter galaxies selected at any epoch quench earlier. So you can kind of see this by the difference between the pink and the navy line. And Pablo looked into what exactly determined which galaxies of this broader submillimeter population quench early, and he found that the early quenchers tend to experience an early major merger. So this is just a summary of my talk. First of all, using simulations to try and understand how robust our observational inference methods are, and then Pablo's work on recalibrating the L galaxy SAM. So I'll take any questions. Thanks very much.
I think the work by Pablo is very interesting. Could you elaborate a little bit on the rule that he uses for black hole growth? Does he just use the black holes in TNG, first of all? And then does he try to draw a conclusion, his own conclusion, between the black hole size and the state of quenching?
Yeah, so firstly, so Pablo hasn't used TNG. He's using the L galaxies semi-analytic model. So he kind of calibrates these subgrid relations, and yeah, you get kind of slightly different relations on, for example, how efficiently the cold gas accretes onto the black hole, depending on the observational constraints that you put in. So yeah, we show in the paper kind of the different models, and then also the predictions for the black hole mass function, which actually do differ quite a bit between its models. And then, relation between the black holes, black hole size. You asked.
What's the rule? You've got a black hole.
Yes.
Does it quench? Why?
So yes. So yeah, the ones that quench early, where did it? Sorry. So the ones that quench early have basically very efficient early accretion onto the black hole. So you grow it, and then it manages to keep the gas hot. Because they come out kind of significantly overmassive compared to the kind of black hole stellar mass relation, black hole mass stellar mass relation. The ones that quench early. Yeah.
All right, great. Why don't we thank Rachel one more time?